In this video, I'm going to try and compare and contrast some of the concepts and vocabulary surrounding these different kinds of energy we've been talking about in Chapter 12. To begin with, we've got three different kinds of energy that we're talking about. There's H, which is enthalpy, S, which is entropy, and G, which is free energy. And I'm going to go through them one by one. Beginning with enthalpy. Enthalpy is the heat energy in a chemical system. This is talking about the types of energy that are stored in chemical bonds, that are stored in intermolecular interactions, and that are expressed in molecular velocities, those kinetic energies. We have two typical terms we associate with that. The first is for positive delta H, so an enthalpy increase inside a system. Those are endothermic processes. They absorb heat energy, raising the internal energy of a system. This is associated with energy transfer from the surroundings into the system. The opposite term is for a negative delta H. This is exothermic. These are systems where energy is being transferred from the system to the surroundings. Heat is coming out. So let's contrast that with S, entropy. Entropy is the energy associated with available microstates, and a microstate is just a given way that a system could arrange its components. You can also think about it in terms of freedom of disorder. It is all of the energy that we really can't talk about being expressed as a thermal type of energy. So that's another way you can think about it. We don't have any particular jargon for talking about positive or negative entropy changes. We just talk about an entropy loss or an entropy gain. A positive delta S is an entropy gain, and these types of processes tend to be more spontaneous than negative delta S processes, so entropy losses. As a matter of fact, you can have processes where both the system and the surroundings are gaining entropy at the same time. You don't have to overtly transfer entropy from one place to another. An example of this would be mixing together two chemicals that generate heat when they mix. The system is the two chemicals mixing. That mixing is an entropy increase all by itself, but then the heat absorbed by the surroundings is going to increase the entropy in those surroundings as well because of the greater freedom of molecular motion. Let's get into that last kind of energy then, free energy. Free energy is all of the energy available in a system to do work, and that encompasses both these heat or enthalpic and these entropic contributions that we've been talking about. And we have two vocabulary terms associated with that. The first is for positive delta G processes. These are non-spontaneous. These have an energy cost to them, which means that they will not happen unless you feed in that energy to fuel that process. And a great example of this is photosynthesis. Photosynthesis turns water and carbon dioxide into sugar. And that process will not happen unless light is shining on that leaf, providing energy. The flip side of that are negative delta G processes. We call those spontaneous because they will happen without any outside intervention. And negative delta G processes are spontaneous because they are processes in which universal entropy always increases. That's actually the underlying phenomenon that makes it spontaneous. So, a great example of a spontaneous process would be combustion or metabolism. Both of those will happen without energy being fed into the system, and that makes a lot of sense because we could not gain energy from metabolism if it was non-spontaneous. We would have to put in more energy than we would get out. And as a final connection between these concepts, while delta G is the final arbiter of spontaneous versus non-spontaneous, we can kind of associate these two states with delta H or delta S values. So positive delta H's, endothermic processes, and entropy losses, negative delta S's, tend to be associated with non-spontaneous processes. On the flip side, spontaneous processes tend to be associated with exothermic, negative delta H, or entropy gaining, positive delta S processes. And this is because the universe overall is trending towards minimizing spikes of internal energy. They want to distribute the enthalpic energy in the universe as broadly and evenly as possible and maximize the overall entropy of the universe. And exothermic processes and entropy gains are associated with that goal. So, to quickly recap, delta H is talking about enthalpy changes, heat flow. Delta S is talking about entropy changes. This has to do with molecular rearrangement and available microstates. Delta G covers the contributions from both of these things and ultimately tells us whether or not something is going to be spontaneous or non-spontaneous. So, I hope that cleared a few things up. I will see you in class.